problem 3.4. All right, let me find it here. A dormitory at a large university built 50 years ago has exterior walls constructed of LS equal to 30 millimeters thick sheathing with a thermal conductivity of Ks equal to 0.1 watts per meters Kelvin. To reduce heat losses in the winter, the university decides to encapsulate the entire dormitory by applying a Li 30 millimeter thick layer of extruded insulation characterized by a thermal conductivity of 0.029 watts per meters Kelvin to the exterior of the original sheathing. The extruded insulation is in turn covered with an LG of 5 millimeter thick architectural glass with a thermal conductivity of 1.4 watts per meters Kelvin. Determine the heat flux through the original and retrofitted walls when the interior and exterior air temperatures are T infinity I is equal to 22 degrees Celsius and T infinity outer is equal to 0 degrees Celsius, respectively. The inner and outer convection heat transfer coefficients are 5 and 30 watts per meter squared Kelvin, respectively. All right. So we're given a dormitory wall. The dorm exterior wall. There's sheathing, and that gives us a thickness 0.03 meters. Thermal conductivity for that sheathing is 0.1 watts per meter Kelvin. Then when it's retrofitted, we have some insulation. The insulation is 0.03 meters. Thermal conductivity 0.029 watts per meter Kelvin. And then we have some glass, architectural glass, which is a thickness of 5 millimeters. And a kg of 1.4. We have T infinity inner is 22 degrees Celsius with a convection coefficient of 5 watts per meters Kelvin, or meter squared Kelvin, sorry. And we have the outer is 0 degrees Celsius, convection 25. And they want us to find the heat flux through the original and retrofitted walls, okay? All right, so we need to draw our schematic. So here's our sheathing, length, insulation, glass. All right, so we have sheathing, insulation, architectural glass, and we have the convection on the inside and outside of it. So the original just has sheathing. The retrofit has where we're adding the insulation and the architectural glass. Okay, so where do we begin this problem?
Start off by finding the thermal resistance.
So the thermal resistance. So thermal resistance, just the values, or
Like an equation of some sort, so that we can use that to find heat flux.
yeah, I mean that is our steps we're going to do. But before we even do that in these type of problems, what is the first thing we do here?
Verify that it's 1D steady state constant properties.
All right, we're gonna, yeah, we can do that. Let's do, so valid that it's got its steady state, constant properties, and then no thermal generation. It's a negligible contact resistance between those two layers. And 1D, right? All right, so that allows us to get those equations. But there's actually still one more thing. So since we now know these assumptions and we want to do resistances to solve for heat flux, but there's one more thing we need to draw first.
Thermal circuit.
Yeah, so we start off knowing we can do these things right here, right? Then we can draw a thermal circuit. Okay, that simplifies the question. So we start there then. So if we look at the originals, how many, so the original, before it was retrofitted, how many resistors do we have in this network or in the circuit?
Was it just the first one?
Yeah, of the layer. So they'll be the first, so you'll just have the sheathing.
Yeah, so just S.
So, but how many resistors then?
2 resistors.
3, so there's 3 resistors then, because convection has a resistance to it also.
So it's going to be 2 convection and 1 conduction, right?
Yeah, okay,
Okay.
so the original then, and this will be our resistance from convection inner, And then we had our resistance from the sheathing, our resistance outer from convection. Okay. All right, the last thing we draw on our thermal circuit is just like our heat flow, right? So where is that going?
From T infinity I to T infinity O.
Yep, from our high to low in this case, and we have this way. And I'm doing heat flux because we have a plane wall, and they didn't give us anything about cross-sectional area. Okay, so then it just asked for heat flux, right? So it asked for heat flux, and we don't have any cross-sectional area that this heat is flowing through, okay? And it's the same cross-sectional area because it's a plane wall. Okay, so that means it's the same heat flux to the left, to the right. Okay, so the same heat flux is what's going through the whole thing. All right, retrofitted. How many resistors do we have with the retrofitted wall now?
5.
5, okay. Two, 3, 4, 5. All right, I can still count. All right.
For those resistances, are 2 of them convection and 3 of them conduction then
Yep.
in this case?
Mm-hmm. Yep. Yeah, so we have then our convection on the left, sheathing. Then we have the insulation, right? And then we have the glass. And then we have our outside convection. And this was heat flux original here. And now we'll have our heat flux for the retrofitted there. Okay. So then earlier before we did the assumptions in thermal circuit, I heard calculate the resistances, right? So we can set that up. So we have our S. Oh, this should be not just RI twice. Let's call that INS instead. For the insulation. All right, so these are the resistances that are for heat flux, so they don't have the area term in them. So in this case, inner for convection is just 1 over HI. For conduction of a plane wall, we just have L over K. So we can do that for each of those, and then we have our convection on the outside. And then I don't have these individually calculated, but we have all these were given to us. So we have all these properties were already given in the problem and why the paragraph was so long. And so we can calculate these. All right, so let's say we have those values calculated. What would be the next step?
Add them up because they're in series.
Yeah, so they're series resistors, so we can add up our resistances. So our total of the original is Ri plus Rs plus Ro. And our total retro is this, okay? And I don't have, again, the numbers individually. I didn't end up calculating in between, but we could do that, okay? And I suggest when you do the problems that you do that, or at least step through like this. Okay. Now what? Say we have the R total.
And then heat flux is T infinity 1 minus T infinity 2 divided by R total.
Yep. So we have the original T infinity inner minus T infinity outer divided by R total original. And then our retro, same temperatures that it's across, okay, because it's the same air temperature being controlled on the inside of the dorm, and then the same outside temperature. Which one do we think is going to have a lower heat flux, the original or retro, and why?
The retro, because it has a higher resistance.
Yeah, so anytime you're adding additional resistances, you're going to lower your heat flux, right? Because they both have this resistor, you have your sheath, and they have this. So we're basically adding these two resistances together, which are positive quantities. There's no negative there. So it's going to lower our heat flux. So original we get with what's given, end up going through, running the numbers, boop, boop, beep, boop, and calculating them, and you get 41.3 watts per meter squared. And then retro, you end up getting 14.0 watts per meter squared. Okay. Okay, so we see the added benefit, right? And if you remember, we did something, thermo 1, let's say, something a little bit probably in thermo 2, is, we had, air conditioners, or we had heat pumps or refrigerators, and, the refrigerated space would be losing heat, or gaining heat from the outside environment, or a heat pump would be losing heat to the outside environment. And we would have to calculate that from other things. With now a idea of heat transfer, you can get a value of what that heat loss is, or heat gain, just by knowing what's going on in your insulation. Okay. All right. Let's see, what do we got time-wise? All right, so let's start on another problem here. Let's do, unless there's some other questions, that one. All right, so let's do 3.47. Another problem where I get to read a bunch. All right, composite cylindrical wall is composed of two materials of thermal conductivity, Ka and Kb, which are separated by a very thin electrical resistance heater for which interfacial contact resistances are negligible. And then they give a schematic. And then the liquid pumped through the tube is at a temperature of T infinity I and provides a convection coefficient Hi at the inner surface of the composite. The outer surface is exposed to ambient air, which is at T infinity outer, and provides a convection coefficient Ho. Under steady state conditions, a uniform heat flux of Q double prime H is dissipated by the heater. Part A is sketch the equivalent thermal circuit of the system and express all resistances in terms of relevant variables. B is obtain an expression that may be used to determine the heater temperature TH. And C is obtain an expression for the ratio of heat flows to the outer and inner fluids. So Q prime, QO outer prime over QI inner prime. How might the variables of the problem be adjusted to minimize this ratio? All right, so we have a composite cylindrical wall. We have a material A, and that gives us a thermal conductivity Ka. We have a material B, and that has a thermal conductivity Kb. And they're separated by a very thin electrical resistance heater. So we have a very thin electrical resistance heater. And they tell us the interfacial contact resistance are negligible. We'll put that in our assumptions. And it's a steady state, and then everything else is really in our schematic. Okay, so let's have fun drawing this one. All right. Oh, first let's do the finds. All right. All right, so they want us to find part A is the thermal circuit. Part B is an expression to solve for the heater temperature, which is TH. And then part C is the ratio of heat flows to the outer and inner fluids. So that's this ratio. And they ask, how might the variables of the problem be adjusted to minimize this ratio? So how might we minimize this ratio? Question mark. Now I'll draw the schematic. All right, so we basically have this tube, okay? Let's put some dimensions in here. So this one is R1. R2. R3. All right, so we have two materials. So we have our material A on the outer side, so that would be here. So that would be KA. Then we had material B is on the inner material. And then on the outside, we have a convection coefficient in T infinity. But we also have on the inside a convection coefficient and a different T infinity. And then we have a heater that's in between material A and B. Okay, so right here, is in between material A and B. And that has temperature TH and a heat flux. Just make sure I'm not missing anything. Nope, that's it. So there's an internal flow and an external flow, right? All right, so with this, we have internal flow, external flow. We have these material A and B, a thin heater in between. First part is to draw the thermal circuit. Okay, so to draw a thermal circuit, we have a few things that have to be assumed, right? So what are those assumptions?
Steady state, one-dimensional, constant property.
One-dimensional constant properties. And then there's one more. What's the last one?
Negligible
No,
contact resistance.
Not we can include contact resistance, but in this one it's negligible. But there's one more thing, so we can do a thermal circuit.
Negligible
energy.
thickness of the heater.
Energy generation.
Yeah, so it's no energy generation. And that it comes from the thickness, right? Energy, and I'll talk about that in a second. Because and then we still have negligible contact resistance. All right, so we have these four assumptions and then also negligible contact resistance. So part A says we can do is thermal circuit, right? And thermal circuit, no thermal energy generation, although we have a electrical resistance heater. So I mean, there's electrical energy coming there. So that is typically, again, that would be energy generation. To use a thermal circuit means there's no energy generation. So again, we have something there to be careful of. Okay. All right. So if we're looking at the thermal circuit, let's start there, and then when we'll draw it, we'll talk about it again about that heater. Is how many thermal resistances do we have?
Five.
5.
5. Okay. All right. So let's start from the inside to the out here. So we have T infinity inner. And then we have the conduction through material B. Okay, and then to have 5, that means you guys are having a resistor, another resistor thermal resistance for the heater. And in actuality, we can assume there's no resistance there, and we have to make an assumption to go along with it, and they kind of tell us, because they're actually trying to they tell us it's very thin, and they give us in the schematic that the heater's at just pH. Okay, so that means it's very thin. They're saying it's at the same temperature if it's very thin. So we're going to have an isothermal heater. Okay. So that means that is pH right there. Let's try that in red. And we have another resistance. So actually, let's do this is resistance inner. This is our material B. Then we have A, and then our convection on the outside.
Professor, can you go back to the schematic real quick?
Mm-hmm.
So when there's When we're going from R1 to the material to R2, is there not going to be a resistance that's developed there? Or is it just the same material?
So from R1 to R2, that is all material B.
So like from
So this
radius
is
0
material
to
B.
R2.
Somewhat? Sorry.
What about from the center out to R2? Do we have a change of material that way?
From the center. From here?
Yes.
That's convection.
So it's convection from that point out to R1, and then R1 to R2 is going to be conduction?
Yep.
Okay. All right. I thought that there was, I don't know why I thought there was going to be an extra form of conduction happening in there, but okay, that makes sense.
Yeah, there's just moving, it's a tube with moving fluid through the center. So that tube then has a T infinity to it, that fluid.
Okay. Thank you.
Mm-hmm. This is our material A. All right. So now we need to draw on the one last thing. What else do we need to draw on our thermal circuit? What else did we have here on these?
The heat flux.
Yeah, so in this case, it's heat because we're dealing with the cylindrical coordinates, so we can't just divide out the area. But where do I draw?
From the inner going out.
Yeah, so basically we have the QH from the heater, right? And that's what's going. So these all should be per unit length. Sorry. Because we don't have any lengths given to us on this. And so some of the heat goes to the inside fluid, and some of the heat goes to the outside fluid, and it's all coming from the heater. Okay. Part B is the expression to solve for TH, but we'll leave that. We'll run out of time today, so we'll finish this one, and then we'll do one more the next class, and then we'll move on to like heat sinks, basically extended surfaces within chapter 3. Okay. So that's it for today. Okay, so if you have any additional questions, let me know. You have your second homework due tonight if you haven't completed it yet. So get that done. All right.
I had a question from the last lecture.
Yeah, what's up?
For the example we did of the 2.38 with the boundary conditions.
Okay.
And then you said, certain conditions come from, the convection COE, the constant heat flux. Is that stuff that just we should know, or we would have needed to do that to get those conditions?
I'm not sure I'm following. There's boundary conditions, and those are in the table, right? That table 2.2. And you can determine your boundary conditions just by looking at what's going on. Like even in this problem, you can determine there's convection on the outside surface. Like you can, just by your schematic of what's happening, you can determine your boundary conditions.
Okay.
All right, does that make sense?
Yeah, and I think that what you said about the table, maybe I had missed that.
Yeah, there's a table 2.2. It's also one slide in our lecture slides that just deal with boundary conditions and show the 4 boundary conditions of, constant temperature, constant heat flux, convection in the adiabatic or, the symmetry one. So there's those
Okay.
4 boundary conditions.
So it's based on that condition, like in your schematic, you can then utilize a specific equation.
Yep.
Okay, that makes more sense now.
All right. All right. So then that's it. You guys have a good rest of your week, I guess. So we'll meet back here on Monday. All right.
Sounds good.
Good
Have a
one.
good night.
Thank you.